Hi, I'm Pradeep Subedi. I'm currently working as Research Associate at Rutgers Discovery Informatics Institute. Today, I'll be talking about scientific workflows, data-related challenges in scientific workflows, and how at Rutgers we have tackled challenges of data management for extreme scale in situ workflows. End-to-end scientific workflows include coupled simulations along with data handling or processing services such as analysis and visualization. Running at extreme scales, these workflows can produce insights into complex phenomena with increasing fidelity. However, the execution of the simulations on leadership class systems presents significant data management challenges due to the increasing volume of data that has to be managed and moved. This data can be in the order of petabytes. For example, the XGC-1 gyrokinetic particle in-cell simulation workflow can generate up to 100 petabytes of data in a single run on leadership class systems such as Titan and Summit. These large datasets then have to be carefully processed and analyzed before scientists can derive insights from simulations and better understand the phenomena being modeled. However, moving such large volume of data between the simulation and analysis components of the workflow quickly becomes a serious bottleneck. Traditionally, large volumes of data generated by simulations are dumped to storage file systems, and other applications such as analysis or visualization analyze or process the data to extract scientific insights. However, as systems scale and application complexity grows, I/O becomes recognized as a severe performance bottleneck for coupled scientific workflows, and it impedes the scientific value. While simulations generate ever larger data volumes to be analyzed or visualized, there is an increasingly large disparity between the I/O and computational capabilities on most high-end computing machines. Factors such as contention for shared resources and complicated I/O patterns further impact the attainable I/O performance on those platforms. The combined effect results in undesirable situations where a substantial portion of the simulation runtime is spent in writing data to the storage system. To maintain I/O overheads at a reasonable level, data only in selected time steps are saved to storage system, and as a result, the data pertaining to intermittent phenomena is lost. This adversely affects the scientific discovery. As a result, the traditional file-based coupling approach becomes infeasible and cost-prohibitive, especially for future architectures of HPC systems. To address the costs of data movement, various runtime data management approaches have been designed and developed to support coupled simulation workflows, which have the potential to accelerate the overall time to solution process. These solutions leverage in situ processing, that is, for these workflows, some of the operations can be performed without moving the data to and from storage. These operations are thus performed in situ or in place. The advantage of in situ processing is it allows the I/O pipeline to bypass a large portion of the output and input overheads associated with accessing the storage backend. The most common in situ processing technique is in situ visualization or analytics, where the data is prepared and visualized or analyzed without I/O to disk. By holding the data on the node where it is generated and producing the visualization at the same node, the potential bottlenecks that arise from data movement are further alleviated. However, emerging end-to-end scientific workflows require support for data-intensive couplings between heterogeneous processes. These applications can run at different spatial and temporal scales, at different levels of parallelism, at different times, and possibly at different locations. And as a result, these couplings have to be dynamic, flexible, and often asynchronous. Efficient and scalable support for such coupling behaviors and associated interaction and coordination patterns present several challenges. For example, coupling data between applications or application components that run on distinct resources, and these resources can be clusters or parallel machines, will often result things running on different number of processors, and it requires efficient data transport and data redistribution. Furthermore, communication and coordination patterns often depend on the state of the computation and are only known at runtime. This requires that the communication schedules are efficiently determined at runtime without imposing synchronization or the collection of global information about the data distribution. Similarly, monitoring or analysis components, possibly dynamically instantiated, may require efficient access to the data or data subsets of interest that might be independent of the data distribution or the local representation. Finally, data may often have to be transformed before it is consumed, and this transformation has to be performed in situ. To tackle the data management challenges, we at Rutgers have designed Data Spaces. Data Spaces is a data staging framework that provides a flexible interaction and coordination via simple high-level abstractions that can support the dynamic and asynchronous data-intensive coupling patterns required by the scientific workflows. Data Spaces provides the abstraction of a semantically specialized, distributed, virtual shared space that can be associatively assessed by all application components and services. It enables live data to be extracted from running simulation components, indexes this data online, and then allows it to be monitored, queried, and assessed by other components and services via the space using semantically meaningful operators. The Data Spaces design enables it to be scalable and efficiently implemented on and across various high-performance systems and clusters, and it can be used by application components to efficiently realize a variety of dynamic coupling behaviors. Data Spaces is currently utilized in various extreme scale applications as part of ECP, which is Exascale Computing Project managed by Department of Energy. However, emerging architectural trends indicate a decrease in the amount of DRAM memory per core, as well as the slower rate of increase in storage bandwidth as compared to the computational throughput. These trends will severely limit the effectiveness of memory-based staging solutions, which enable in situ workflow execution and allow applications to tolerate slower disk latencies. The rate of data generation is just one challenge, which is putting pressure on in-memory staging solutions for in situ workflows. Even if the simulation application is not generating data at an extremely high rate, coupling or data analysis may require data accumulation over multiple simulation iterations, causing the data flowing between the components of the workflow to grow quickly. With limited memory sizes, this intermediate data will have to be offloaded from in-memory staging, possibly to the parallel file system. However, the increasing latency gap between disks and memory makes such solutions undesirable. Systems at leadership computing facilities are increasingly augmenting the hardware and I/O middleware layers to better handle applications with bursty I/O by attaching a set of on-node NVMe solid-state drives, and these solid-state drives are often called burst buffers. Emerging non-volatile memory technologies have smaller SS latencies and better throughput as compared to the parallel file system, and can therefore be used as an intermediate tier of the memory hierarchy. This tier of on-node NVMe solid-state drives can enable data staging services to offload data from staging memory without incurring the performance penalty associated with moving it to the parallel file system. While these burst buffers are designed to act as a right-behind cache for HPC storage systems, integrating them as a part of memory hierarchy for data staging presents new challenges. Although burst buffers have higher throughput than conventional disks, they have a much longer SS latencies and a lower throughput as compared to main memory. In an application workflow, if component of the workflow must access data offloaded to the burst buffer tier, it will experience a higher latency, which can significantly impact the performance of the application. Intelligent data prefetching based on SS patterns can hide disk access and data transfer latency by moving the data to DRAM before it is requested. The effectiveness of such prefetching, however, depends on the ability to recognize data access patterns and identify appropriate data to be prefetched. Existing prefetching approaches for coupled scientific HPC applications have been based on user-defined hints. While this works for simple applications, as application workflows become more complex, and this approach quickly becomes infeasible. Furthermore, SS patterns can change at runtime. The workflow may include third-party libraries where the SS pattern is not known to the user, and staging resources may be shared between multiple application workflows. These factors make it likely that user-defined hints will be of little use or even detrimental to performance in complex application workflows. Since prefetching the wrong data to incorrect hints degrades the performance, the additional data movement will be detrimental. At Rutgers, we have explored machine learning-based approaches to capture these data access patterns between components of staging-based application workflows. To use these learned access patterns to move data between storage layers of the staging service, the staging servers are run in an autonomous manner. Rather than modeling individual applications and their access patterns, we model the data accesses between multiple components of application workflows. We do this because in the case of application workflows, access patterns of the different components applications that make up the workflow and from different workflows sharing the staging resources can be interleaved at the staging servers, and as a result, accurately modeling an individual application's access pattern is not sufficient. We have specifically explored NGRAM, which is a grammar-based machine learning models to dynamically manage and optimize data movement across multiple layers of the storage hierarchy and across staging nodes. Specifically, incoming read requests to the data staging servers are tracked at runtime to build NGRAM models. These models are used to anticipate future requests for prefetching data objects from SSDs to DRAM. This reduces application perceived SSD-SS overheads and improves the overall data read time. We implemented and deployed Stacker, which is for data movement across memory hierarchy on top of Data Spaces Framework on Caliburn supercomputer at Rutgers and Titan Cray system at Oak Ridge. We have also used the knowledge about the application access patterns to design and deploy Destiny, which dynamically anticipates which data the consumer wants, at what time, and preassembles or packages the data and brings it to the staging node that is closest to the consumer. When data staging processes and consumer processes are co-located, Destiny removes the need for inter-process communication by making these data available to the consumer as shared memory objects. When the consumer application process is located on a separate node from the staging server that it is attached to, Destiny marshals the data in the format that the consumer is likely to access it. This enables Destiny to amortize the costs of data discovery and data fetch operations. All of these researches that we have described here regarding in situ workflows and machine learning techniques have been made open source in GitHub. To know more about data spaces and ongoing research, you can visit www.dataspaces.org. Thank you.